Hey guys, this is the third video for the part B for chemical bonding, where we are going to continue with metallic bonding. So metallic bonding occurs when a large number of metal atoms interact. So unlike the reaction between metal and non-metal involve the electron transfer, when two metal atoms interact, they can also share their valence electron in a covalent bond and form gaseous diatomic molecule of M2. So the electron C model of a metallic bonding proposed that all metal atoms in the sample contribute their valence electron and form what we so-called as electron C. So as you can see inside the diagram in here, these are all the electron C's contributed by the metals. Okay, and the metal ions are submerged with these electrons in the C in an orderly array. So the model which we use to study the metallic bond is called as a band theory, because it stated that the delocalized electron move freely through the bands, forming an overlapping molecule orbitals. Now consider magnesium as example. The electronic configurations of the magnesium is 1s2, 2s2, 2p6, 3s2. So each atom has two valence electrons with the 3s. So the closely spaced field energy levels that made up of the valence band, so the upper half of the energy level corresponds to the empty delocalized molecular orbitals, is called as a conduction bands. Whereas the bands filled with the electrons is called as a valence band. So this is what it means by where the differences between the bands. So this is the valence band, which is filled with the valence electron, and this is the conduction band filled with the empty orbitals. So we say that conductivity activity takes place when the electrons from the valence band are able to excite easily for conduction band. So for a conductor, there is no energy gaps between the valence band and conduction band, and electrons can be easily moved to the conduction band anytime. So theoretically, greater the number of the valence electron in the metal, greater the number of electrons delocalized, higher the conductivity. However, conductivity decreases with temperature as the vibration of the lattice ion impede the free movement of the electron in the conduction bands. Semiconductors are elements that normally are not conductor but will conduct electricity at elevated temperature or when combined with a small amount of certain other elements called as dopant. So these elements are usually metalloids such as silicon and germanium. So it says that in a semiconductor, energy gaps between the conduction band and valence band of their solid is much smaller compared to that of insulator. If the energy needed to excite electron from the valence band into the conduction band is provided, solids will become a conductor. So note that this behavior is opposite than that of the metals. Adding impurities or doping to a semiconductor will also increase the conductivity of the semiconductor. So doping can be done by adding one of the following. So you have a dopant of atom containing fewer valence electron called as p-type, a dopant of atom with valence electron called as m-type. So examples of the p-type are in here are boron, and example of n-type are adding phosphorus. Okay. And finally, insulators are substances that does not conduct electricity no matter how high the temperature is applied to the substance involved. The energy gaps between the conduction band and valence band are very large, hence regardlessly how much energy you apply, so it will not able to conduct electricity nor heat. Consequently, much energy is needed to excite an electron into the conduction bands. So lack of this energy, electron cannot move freely. Therefore, glass and woods are insulator, ineffective conductor of electricity. So this is what we talk about the energy gaps between a semiconductor and also an insulator. So that is all for the metallic bond. For the final, we are going to continue with the intermolecular forces, van der Waals forces, and also hydrogen bond. So the nature of the states, matter, substance, and their changes are due to primarily to the forces among the molecule. So both bonding, intramolecular forces, and intermolecular forces arise from the electrostatic attraction between the opposite charges. So bonding forces are due to the attraction between the cation and ion, which is also known as ionic bond, nuclei and electron pair, which is also covalent bond, or the metal cation and delocalized valence electron, which is also known as metallic bond. Whereas intermolecular forces, which we are about to discuss in here, on the other hand, are due to the attractions between the molecules as a result of partial charges or the attraction between ions and molecules. So the two types of the forces differ in magnitude and forces, which explain why bonding forces are relatively strong, while intermolecular forces are relatively weak. So these are the examples of the bonding forces. So in here, in ionic bond, you see that they can all have high energy in here, bonding energy. Whereas in forces, so they are relatively weak and lesser than 1000. Okay. Okay, so let us introduce what is induced dipole or dispersion forces. Consider how a helium atoms, a monoatomic gas we have dipole moment equals to 0, interact with the following species. We have helium interacting with cations. So in here, somehow in some way, helium will shift its electron density to cause it to form temporarily a partial negative and partial positive. So the partial negative part will attracted to the cations involved. And then for hydrogen fluoride, since hydrogen bears a partial positive while fluorine bears a partial negative, so helium will try to force itself in order to attract to the partial negative to form a partial positive charge in here, or in here it forms a partial negative. So in between helium and helium, which is two nonpolar, so both of them will cooperate to form a temporary dipole that influence one to another. So all these type of the temporarily formed dipole, we call them as what we call as an induced dipole. A dipole which is formed temporarily in order to interact with other species. So from the diagram we can tell that if an ion or polar molecule is placed nearby an atom, the electron distribution of atom is distorted by the forces exerted by the ions or polar atoms, resulting in a kind of dipole. So dipole in the atoms or non-polar molecule is to say to be induced dipole, where separation of positive-negative is due to proximity of an ion or polar molecule. However, weak attraction interaction between a non-polar molecule to another non-polar molecule are unlikely to place near an ion or molecule. So between the two non-polar, the forces they form among themselves a short induced dipole, hence each of them attracted temporarily. So that is why their forces are very weak and can be broken. Such interaction is sometimes also known as the London forces. So this is given to you a series of the homologues of the alkane. Okay, you have methane, ethane, propane, butane, pentane, hexane, heptane, and octane with their relative molecular mass. So as you can see, the relative molecular mass increase. So boiling point also increase accordingly. This is due to all these non-polar covalent compounds are influenced by the relative molecular mass or molecular size. So we say that at molecular mass or molecular size increase, the weak van der Waals forces also increase. However, for some of the molecule, especially organic molecule, which have the same molecular mass and functioning group, they have different boiling point and depend on their molecular structure. So for example, C5H12 has 3 isomers, 2,2-dimethylpropane, 2-methylbutane, and N-pentane. However, even though they have the same molecular mass, but their boiling point are very different. This is due to, we say that a straight chain has a greater total surface area compared to a branch chain. So we say that total surface area increase. In another word, a straight chain molecule has a greater total surface area compared to a branch chain molecule. So greater the total surface area, greater the weak van der Waals forces, higher the boiling point of the molecule. The next forces is the dipole-dipole forces. When polar molecules lie near to one another, as liquid as a solid, their partial charge act as a tiny electrical field that orient them and give rise to dipole-dipole forces. A positive pole of one molecule attracts the negative pole to another. So there are forces that give polar covalent a high boiling point and the non-polar than a non-polar compound. So no matter is in solid form or in liquid form, the partial positive will always interact with the partial negative. So this is the second factors that will influence the weak van der Waals forces. So we are now comparing a few organic molecules, all of them with almost the same molecular mass. However, their dipole moment are different. So you can see that as the dipole moment become greater, the boiling point become the dipole-dipole moment, the dipole-dipole attraction forces here become stronger and hence increase their boiling points. So this is the second factors that will influence if they have almost the same molecular mass. Last but not least, you have hydrogen bond. So hydrogen bond is a special type of dipole-dipole interactions between the hydrogen atom in a polar bond, such as NH, OH, or FH, with an electronegative element such as O, N, or F. So diagram below show a few examples of interaction between molecules using hydrogen bond. So this is between hydrogen bond. This is another hydrogen bond. This one. and this one too. So all of them are called as a hydrogen bond because hydrogens are interacting with the oxygen. Now it is called like a bond because their forces is almost as strong as a bond. So that is why hydrogen bond. So really we study the effect of the hydrogen bonds towards the molecule. So as you can see in here, these are group 14, 15, 16, 17 hydride. So let's start from the trend of the group 14 in here. As you can see from the group 14 in here, so when going down to the group, so it says that molecular mass increased, the weight van der Waals increased, that is why the boiling point increased. Now the same trend can be explained as in pH3, ASH3 and also SPH3. So in here similarly, if they have the boiling point molecular mass, so greater the weight van der Waals forces, higher the boiling point. However, for ammonia, see why ammonia has a stronger hydrogen bond. This is due to ammonia can form hydrogen bond in between them. So as a result, it can form it has a higher boiling point compared to other group 15 hydride. Now, if you were to compare between the hydrogen bond, so hydrogen fluoride is to say has a stronger hydrogen bond compared to the ammonia because F is more electronegative than N. So the hydrogen bond between the FH is stronger than NH. As a result, it has a higher boiling point. As for H2O, so H2O is to say has the highest boiling point even though F is more electronegative than O and the hydrogen bond between FH is stronger than OH. However, water forms more hydrogen bond compared to hydrogen fluoride. That is more, it has a stronger hydrogen bond. So the factor hydrogen bond can also be used to explain solubility of some organic compound like water. Ethane cannot dissolve in water, but ethanol can dissolve in water due to the formation of the hydrogen bond. So same goes with ethanoic acid, which can also form hydrogen bond. So some organic compounds form dimer using hydrogen bond. For example, glacial ethanoic acid is dissolved in organic solvent. We form dimer by using hydrogen bond to interact in here. So in some cases, hydrogen bond can also use as an intermolecular forces. So 4-nitrophenol is to say has a higher boiling point compared to 2-nitrophenol because the hydrogen bond is used as intermolecular forces, while for 2-nitrophenol, hydrogen bond is used as intramolecular forces. So that is why 4-nitrophenol has a higher boiling point. So with that, we end for our chapter 3. So we see you on the next chapter. Thank you.